Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ont. In this tutorial video, we'll go through this November 2022 fairly recent paper for this Cambridge International IGCSE Chemistry Extended. This is paper 4 variant 3 and it's a 1 hour 15 minutes paper for 80 marks total. In this first question, so we're going to complete this table on some properties about relative charges as well as relative masses. We know that in terms of mass, the proton and the neutrons, they are together called the nucleons. The nucleons are the particles inside the nucleus, which is the center of an atom, and this is where the mass is concentrated. So these are the heavy bit there. The mass is concentrated inside the nucleus, so both of them are as heavy as each other. So the relative mass there is 1 and 1, and in fact we know that electron is about 2000 times lighter compared to the mass of protons compared to the mass of neutrons. These electrons are in the shell, they are outside the nucleus, they are in electron shells outside the nucleus. In terms of charges, we talk about the nuclear charge of the protons and the neutrons. In fact, the neutrons have 0 charge, and this means that the charge inside the nucleus come entirely from the charge of the protons. This is +1. Usually we will write E minus representing the -1 charge of each electron, and we will write P plus representing the +1 charge of each protons. A lot of chemistry to do with electrons, so you will have seen E minus more often than you will see P plus, because protons being positively charged, protons inside the nucleus is not something we typically do for chemistry. That is to do with nuclear physics, to do with the nucleus there. That's it for that 2 marks overall question. Part B, this question is about atoms or ions. We can see that when you have ions, you have the 2+ charge for this calcium ions. So +2, it means that the atom had lost electrons. You have lost negative charge. You have lost 2 of the negative charge. That's why you have 2 extra protons than the electrons. Your number of protons is your identity. It's your atomic number. It's also known as your proton number. Is the number of protons in the nucleus of an atom. It is this number here at the bottom left of this standard international convention there. This number on the top left, the 42, that represents something called the nucleon. The nucleon number, the number of protons and the number of neutrons, also known as the mass number, as they're made out of the things that are as heavy as each other inside the nucleus, together called as nucleons. How many nucleons do you have means how many protons plus how many neutrons you have. So to find out the number of neutrons, what you do is you will do the nucleon number or the mass number, take away the proton number or the atomic number. So here we have 42. So I'm going to take away the number of proton, which is 20, and I'm left with 22 on my calculator. Here, this is chlorine. This is element number 17. So the number of protons there is actually 17. In terms of the electrons, we could see that there is no charge. If there is no charge, we are talking about atoms. If atoms are uncharged, it means that the number of electrons must be equal to the number of protons, because the positive charge get balanced by the negative charge. If you have 17 protons which are positive charge, you must have 17 electrons which are negative charge if you have atom which is uncharged. To work out what is the symbol for the last one, we look at the number of protons. That is your identity. Element number 16. Element number 16 in the periodic table is sulfur. To work out whether it is charged or not, you look at the number of protons and the number of electrons. You could see that there is 18 electrons and 16 protons. So 18 E minus, 16 P plus. You can see there is more negative charge than the positive charge protons. By right, in atom, we should have number of electrons equal to number of protons. So what we could say here, the atom which consisted of 16 electrons must have gained 2 electrons. You gain negative charge, you gain 2 of the -1 charge. This becomes S2 minus. And the number on the top left will be the nucleon or the mass number, which is basically the total number of protons plus the total number of neutrons. So proton 16 plus 16, this gives you 32. So there must be 32 on the top left there, and 16 proton number. The element is sulfur based on 16 protons in the nucleus, 2 minus because you have 2 extra electrons compared to the protons, giving you a 2 minus charge. Overall, there's a 6 marks question. That's it really for this 8 marks first question. In this question number 2, we have a series of these melting point, boiling points, as well as electrical conductivity. These are what you call collectively as physical properties. It's got nothing to do with their chemical reactivity. So these are not chemical properties, these are physical properties. Looking at this melting and boiling point, the first thing I can roughly see is this is negative. Negative values usually mean that these are low. Yes, this is 79, which is positive, but they're still relatively low compared to the rest of the molecules. So I can say that E and also H has low. So E and H has low melting point and boiling point. Most likely we are looking at simple covalent structure. Out of 4 structures in the structure and bonding topic, only simple covalent structure has low melting and boiling point, especially to the extent that these are negative value. They are going to boil at very low temperature. So conduct electricity when solid. So that means you're looking at metals can conduct electricity as solid because you have free moving delocalized electrons. These are not electrons in the shell. These are delocalized outer shell electrons. If you think about the giant metallic lattice structure of metals, this means that we're looking at, yes, that must be metal. So this means D must be metal. There's our second conclusion. D is a metal. And then we say that can conduct when liquid. Previously, this thing doesn't conduct, but now there is one of them that can conduct, but it doesn't conduct before, but now it can conduct. So that means that you must have free moving ions, because this must be giant ionic lattice structure stated in the syllabus for your electrolysis. When you have giant ionic lattice structure, your ions are not free to move in the solid state. They only vibrate in fixed positions, but now they're in the liquid state. They become molten. They can slide past each other. Free moving ions, because there are no electrons on the outside. This is giant ionic structure. It's not giant metallic structure there. Now looking at these, identify the substances which is meaning we're looking at just one, singular, okay? A liquid at 25 degrees Celsius. A liquid mean already melted, but they want a liquid, so not yet boiled. So you haven't boiled yet, so your boiling point must be higher than 25 degrees Celsius, but your melting point must be lower than 25 degrees Celsius. So 25 degrees Celsius must lie somewhere in between, and we're looking at this option E here, because 25 degrees Celsius is in between minus 117 melting point. Higher than that, already melted. Lower than boiling point, has not boiled. So really, we're looking at E as the answer there. A gas at 25 degrees Celsius already boiled by the time you go to 25 degrees Celsius. You can see that H must be what we're looking at, because by 25 degrees Celsius, you're already way past the boiling point. You have already boiled that. Now, solid consisting of simple molecules, but they also talk about solid. A solid consisting of simple molecules at 25 degrees Celsius. So this we're looking at something which is relatively low. So still relatively low. Relative means in comparison, it is still low melting point and boiling point, but it is a solid. So it's a bit higher than this negative value. And we're looking at G really, because in terms of 25 degrees Celsius, that 119 degrees Celsius melting point, despite it being looking quite high, but it's not as high as like thousands or 100 something, but it is still higher than 25 degrees Celsius, has not melted, because at 25 degrees Celsius, lower than melting point. So 25 degrees Celsius, lower than the melting point, which is 119 degrees Celsius. So you have not melted, therefore you are still a solid there. Part B, we're looking at which one is a metal. As I mentioned earlier, we look at conductivity when solid due to the free moving outer shell electrons that have been delocalized. That must be D. So the reason being, only D can conduct as a solid. So that one is due to free moving outer shell electrons that has been delocalized. Or you can say C of delocalized outer shell electrons there. Now identify the substance which has a macromolecular structure. This term macromolecular structure can also be interpreted as giant covalent structure. Sometimes teachers also mention about giant molecular structure. So they both mean the exact same thing. Giant covalent structure, giant molecular structure. Some they call it macromolecule. Not my most favorite word, but they do use it. Give two reasons for your choices. Macromolecular structure, they will have very high melting and boiling point. And we're really looking at breaking a lot of strong covalent bonds. So F will be one of it because it doesn't conduct when solid, it doesn't conduct when liquid. This is covalent structure there. So F must be what we're looking for in terms of, very high melting and boiling point, as you need a lot of energy to break many strong covalent bonds. That's factor number one. So very high melting and boiling point. So they didn't ask for the exact reason. They asked for properties from the table, but the reason is basically you need to break many strong covalent bonds in this giant covalent structure. Reason number two, based on the table, looking at F, it does not conduct electricity when solid, it does not conduct when liquid. It's definitely not ionic, so it does not conduct electricity both when solid and also liquid, due to no free moving electrons. Does not conduct electricity. That's the word I was looking for. Does not conduct electricity both as solid or liquid. So definitely not ionic compound, definitely not giant metallic structure there. Last but not least, we're looking at something which is an ionic solid. So ionic solid means it has giant ionic lattice structure. How does a giant ionic lattice structure look like? You're supposed to be able to describe it as the syllabus say. It consists of alternating cation and also anion. So this is part of a giant structure. So in front, at the back, what else? Top, bottom, left, right in three-dimensional giant ionic lattice structure there. So this ionic compound was identified based on the conductivity when it becomes molten, but not when it's solid. There was substance I, as I mentioned earlier, relatively high, much higher actually, melting and boiling point. But just based on melting and boiling point, we could have easily gone for F, but it's not really just a high melting and boiling point. So they want reason, so they want singular. So it's not just the high melting and boiling point, but the most important factor was to do with it can conduct electricity. It cannot conduct when solid, by the way, because the ions are in fixed position. It cannot conduct electricity when solid, as the ions are not free to move. They are not mobile in the solid state. They only vibrate in fixed position, but conducts when molten, or when liquid, due to free ions being mobile. Mobile means you can become free to move. And that's it really for these 2 marks question to run out these 10 marks overall questions on structure and bonding there. Question number 3, so this is about naming the ore of aluminium, which consists mainly of aluminium oxide. They want the ore, so aluminium oxide is found as an ore from the ground, and this is basically bauxite, Bauxite, straight from the syllabus. Next one, what is meant by electrolysis? So electro, that definitely is to do with electricity. We are passing electrical current through an electrolyte. Lysis, the English word, it means to split. So what we are doing here is we are splitting. So this is breaking up, or you can say decomposition, or breakdown of ionic compound. And this ionic compound must be in the molten or aqueous state. And you decompose this ionic compound into its elements. How do you do it? The most important thing, electricity. So by passing electrical current or electricity, or you can say electrical current or electricity through the electrolyte. The electrolyte is basically the molten or the aqueous ionic compound there. Part C, this is how the setup looks like. We do know that positive electrode this one will attract the negative ions. So it attracts anions, which are negative ions. So this makes this positive electrode as anode. And this negative electrode will attract positive ions. Positive ions are called cations. So if you attract cations, this makes you the cathode and you are negative electrode there. We also know that in electrolysis, we have red cat. Red cat means reduction happens at cathode. We also have another acronym, which is to do with, what am I talking about? Reduction at cathode. Better do one thing at a time. Reduction at cathode, red cat. We also know about oil rig. So rig there stands for reduction is gain of electron there. So overall, the concept is cations go to cathode. Cations are positive ions. Cations get reduced at the cathode based on red cat. Cations get reduced at the cathode by gaining electrons. Our electrolyte doesn't just consist of aluminum oxide, it consists of molten cryolite. This is very important to reduce the energy demand. So give two reasons why you carry it out in cryolite instead of just using pure aluminum oxide. Give two reasons. Well, number one is that this is cryolite. Cryolite helps to decrease the very high melting point of your Al2O3. So as a result of this, therefore, this helps to reduce the energy demand. It helps to decrease the operating costs. And this is the energy demand, which is the operating cost side of thing for the process, therefore making it slightly cheaper, cutting down operating costs. As a chemical engineer, it is your job probably to save your boss some money, so it can make it a little bit less expensive. Next one, write the ionic half equation. So half equation means you gotta balance the equation with electrons. This is at the negative electrode. As mentioned just now, negative electrode is cathode because it attracts positive ions called cations. Cations go to cathode. So we know that this is the red cat, this is the cathode. Reduction happens at cathode. The cations consisted of Al3 plus. Well, I mean, you have the anion O2 minus, but this is the cations. So the cations go to cathode and then it get reduced. Reduction is gaining electrons because of red cat, reduction at cathode, while rig, reduction is gaining electrons. And you're going to get the aluminium as the element. We're going to balance the atom, one aluminium and one aluminium, plus 3 charge. This is no charge, so I do need 3 electrons in order to balance out the charges there. They didn't ask for stat symbol, so we are okay there. But if they did, this will be liquid because you have molten aluminum oxide in cryolite. This is going to be liquid aluminum because you're supposed to have an outlet, by the way, for the molten aluminum to flow out. At the moment, the molten aluminum is just found at the bottom there because there's no outlet for it to flow out from. Now, the positive electrodes are made of carbons. Specifically, you call these graphite electrodes. So the positive electrode attract anions. So this is going to be the anode. Why do you need to replace the anode regularly? For these 2 marks, we're going to write the balance equation. This is the carbon of the anode. This is graphite. It can react with oxygen produced at the anode. And I should probably write this as a second equation because I can probably explain it first. So at the anode, we produce oxygen gas, so oxidation happens, so oxidation occurs. What is the process that occurs at the anode? So that it will be the O2 minus from the aluminum oxide becoming O2, losing electrons like this. Balance the equation, balance the atom first. Because of 2 oxygen, I put a 2 oxide ion. Because of 2 oxide ion, minus 2 for each ion. Minus 2 times 2 is minus 4. No charge for the molecule. I do need 4 electrons there. Having done that, we produce oxygen at the anode. This is the oxygen that you produce at the anode. Reacting with the carbon graphite of the anode, you're going to get CO2. And this is CO2 gas. So anode reacts. The anode, which is made of graphite, it undergoes a side reaction. It reacts with O2 produced at the anode to give CO2. So I could just write the equation, but I'm explaining slightly so they could see that, if carbon undergo reaction as scale as a gas, obviously the anode is going to get smaller and smaller. And eventually when you don't have any more anode, you can't have electrolysis. That's why we do need to replace it after some time. Part D, aluminium is more reactive than copper. So when aluminium is added to copper to sulfate, no immediate reaction is seen. Well, we do know that aluminium being a reactive metal, so Po, So, Ka, Ma, Zil. This is the acronym, Po, So, Ka, Ma, and then Zil, zinc, iron, and lead. And we have hydrogen in between as our reference, hydrogen for this reactivity or acid threshold in the middle, copper, silver, gold. So what happened there is we are saying that aluminium is definitely more reactive than copper. Aluminium by right should be able to displace or kick out copper from copper 2, but it does not occur immediately. This is because we know that aluminium is corrosion resistant for the same reasons. Aluminium has a protective oxide layer. So this protective oxide layer takes some time to be removed unless you rub it with sandpaper in order to expose the reactive aluminium surface. So until this layer is removed, then you're not going to get fresh aluminium reacting to displace or to reduce the copper to copper because it's being protected by this aluminium oxide, which is not aluminium as a metal itself. In part E, aluminium reacts with oxygen to give you amphoteric oxide. So they are kind of giving you the hint in the next part of a question. What is meant by amphoteric? So amphoteric oxide, it reacts with both acid and also bases. It can react with both acid and also bases in a neutralization reaction to form salt and water. So, I mean, when it undergo reaction with acid, is behaving like a basic oxide. When it undergo reaction with a base, is acting as an acidic oxide. Neutralization reaction produces salt and also water. Next one, aluminium oxide reacts with sodium hydroxide, giving you this negative ion. This is one of these many existences or many forms of this kind of ions. And we're going to write chemical equation. So Al2O3 plus this NaOH. I'm going to get this AlO2 minus. So AlO2 minus, and I do have Na plus. So you can see that 1:1 because plus 1 cancel the minus 1 charge. So this thing is balanced out like this because the plus 1 cancel out the minus 1 charge. And the other product is H2O. Is that equation balanced? Not really. We have 2 aluminium courtesy of Al2O3. So we need 2 of that NaAlO2. 2 Na there meaning 2 NaOH. And now I have 2 oxygen, 3 oxygen, I have 5 oxygen. And I have 4 oxygen there, 1 oxygen there, so that's 5. Hydrogen I have 2, hydrogen I have 2. This equation is balanced there. Write a chemical equation. So, they didn't ask us to put down stat symbols, so it would have been okay if I don't put in the stat symbols there. Last but not least, gallium is in the same group. So this is talking about group 3. We're talking about 3 outer shell or 3 valence electrons. And as such, it's going to behave similarly, forming similar compounds. So we know that aluminium plus 3 oxidation number. So gallium is going to be plus 3 oxidation number as well. Hence, you can see gallium 3 there. So meaning to say Ga3 plus Cl minus. 3 and 1 is based on the valency, based on the charges of the ion. Valency is basically the combining power. Depends on how you look at this. The objective is to cancel out the charges. So I'm going to do the LCM, which is lowest common multiple. Lowest common multiple is a primary school mathematics. And I label this how many? How many of this thing on the left? 1 of this thing on the left. So that is 1 of this Ga3 plus. 3 of this thing on the right. So I'm going to write this 3 times. And you can see that the chemical formulation comes down to GaCl3. GaCl3, just like AlCl3. Next up, I will also have Ga3 plus. Sulfate is SO42 minus, having come from sulfuric acid, giving you sulfate salt. 3 and 2. Again, based on the charges of the ion, because our objective is to cancel out the charges of the ion. So when you crisscross, you are doing cross multiply of the charges, and this is how many. I'm going to do the exact same thing. 2 of these gallium-3 plus on the left. As mentioned, 2 of these on the left is how many? So 3 of these on the right. I'm going to write it 3 times because there is no better way of seeing it except for writing it out and seeing it. So 2 gallium. I'm going to use bracket now because this whole thing is SO4 2 minus. When we write formula, we don't show the charge anymore because the charges cancel out. 1, 2, 3. There is 3 whole lot of it. This is called gallium-3 sulfate. So Ga2 and then bracket SO4 3 times. The idea is to cancel out the charges. Plus 3 is plus 6. Minus 2 minus 2 minus 2 is minus 6. Plus 6 cancel out minus 6. Plus 3 cancel out minus 3. Therefore, this compound there, it might be ionic, it might be covalent. Well, we never really know. Probably this gallium-3 sulfate is definitely ionic. But gallium-3 chloride, if you go on to do advanced level chemistry, you will know that AlCO3 has quite a big degree of covalency, but don't want to confuse you anymore there. So that's it for that 2 marks question, and that's it overall for this 15 marks question there. Question number 4, so looks like this is an equilibrium or reversible changes kind of question. We're going to complete this table by using only these words. So, you know, got to read the questions, only these words, yeah? Don't have to come up with new words. So, effect on the rate. So, rate is about how fast, whereas the most commonly associated concept, this is on equilibrium yield. This is to do with how much. How fast is not related to how much, although sometimes they seem to be going the same direction. So what do we know about these reactions? We were not told about this equilibrium yield. Okay. So increasing the temperature means the temperature is getting hotter. If the temperature is getting hotter, the rate should increase. As the kinetic particle theory say, your particles will gain more kinetic energy, they collide more frequently, and so on and so forth. In terms of decreasing pressure, this involves gases. So pressure affects gases. As you squeeze the particle closer together, that is increasing pressure. They will collide more frequently. But this is going the opposite way. This is decreasing the pressure. So that means the particles are going to be further apart, and therefore they collide less frequently, and therefore rate of reaction should decrease. In terms of the equilibrium yield, we can count 1 mole of gas on the left hand side, and then we have 2 moles of gas on the right hand side. So that means that you have greater pressure on the right hand side than the left hand side. So when pressure decrease, what will equilibrium try to do? Equilibrium try to oppose the change. It try to increase the pressure. And how do you increase the pressure? You will go to the side with more gaseous molecule. You will go to the right hand side because the right hand side has more gaseous molecule. 2 moles in total is to 1 mole of gas on the left. And therefore, as you shift to the right hand side, this is talking about equilibrium yield of PCO3 and CO2. This is on the right hand side. So this means that as you shift to the right hand side, the equilibrium is going to give you more of PCO3 and more CO2. Also adding a catalyst will make a reaction happen faster without itself getting changed, without itself reacting. Having reacted at the end of reaction. So overall, there will be no change in equilibrium yield as it only affects how fast and not how much. That's the role of catalyst. Part 2, this table shows that when the temperature increases, then the equilibrium yield of PCO3 and CO2 increases. So this means that when temperature increase, you favor the forward reaction, you favor the equilibrium to the right hand side. So what does this tell you about the conclusion that you can draw from this information? Well, what you can say is that the forward reaction must be endothermic. The forward reaction must have absorbed heat from the surrounding, because if you absorb heat from the surrounding, if I increase temperature, what will equilibrium tries to do? Equilibrium will try to decrease temperature by opposing the change, and you only know how to absorb heat because based on forward reaction being endothermic, you only know how to absorb heat. How do I make the outside cooler? I'm going to absorb more heat from the surrounding. And as I do that, I'm going to favor the forward reaction, and which is why as I shift to the right hand side favoring forward reaction, I'm going to get more PCO3 as well as CO2 there. So that kind of makes sense overall. 2 marks. Next question. This is PCO3 dot and cross. Phosphorus 285 electronic configuration, 5 electrons in the outer shell. You want to share 3 electrons in order to complete outer shell. Chlorine 287, you just want to share 1 electrons to complete the outer shell. So in terms of drawing a display formula, that is personally my favorite usually. I can count. Chlorine will form single covalent bond because it share 1 electron. Phosphorus there want to share 3 electron. Phosphorus form 3 covalent bonds. And phosphorus having 5 electrons in the outer shells. If we show only the outer shell electrons, so that means that you only use 3 out of 5 for covalent bonding. You are still left with 2 more electrons on each phosphorus there. So if I show the outer shell, I have 5 crosses to begin with. And 5 crosses there, 3 of them are being shared. And you're going to form a single covalent bond to chlorine, as chlorine only share 1 electron to the phosphorus. A single covalent bond, this line here represents 2 electrons, 1 from phosphorus and 1 from the chlorine. If I use dot for the chlorine, because there's no right or wrong as long as you use 1 cross for 1 particular element, and then dot for the other one. Now phosphorus there is complete, 1, 2, 3, 4, 5 cross, share 3 from the chlorine. The phosphorus now have fully filled out the shell. Do not forget about the chlorine. You started with 7 electrons in the outer shell, where you only share 1 electron, and now you should be left with 6 more on each chlorine there. So I'm left with 6 more on each chlorine, and you can see that I am just drawing out the 6 remaining electrons, the 6 dots left on each chlorine. If you're doing this on paper, make sure you draw your diagram with pencil so that you'll be able to erase it if something is wrong for that 2 marks overall question. Part C, phosphorus oxychloride has this formula PrCl3. So this is about reading information. It's the only product of this reaction between PCl5 and P4O10. So PCl5 plus P4O10, I am going to get PrCl3. Looking at this equation, I can see this is 3 chlorine, this is 5 chlorine, but they say it's the only product. So we're going to find a way to have 3 and also 5 meet. This is your lowest common multiple from primary school mathematics. 3 chlorine on the right, 5 chlorine on the left, no other position, no other products, no other places for the chlorine to be. So I'm just working out the lowest common multiple, which is going to give me 3 times 5, which is 15. This is the LCM, lowest common multiple. Having done that, I can tell that I must have the 3 going up to 15, so I must have 5 of these. I must have the 5 going to 15. I must have 3 of these. And now, that doesn't make sense at all, does it? Okay, that doesn't make sense at all. Why doesn't that make sense at all? That doesn't make sense now. Okay, I think I have messed up. So that doesn't get balanced. What should I do now? Okay. Alright, that doesn't quite make sense. Okay, I have 10 oxygen, so perhaps I can put 10 here. And now I have 30 chlorine, so I can put 6 there. So 6 times 5 is 30. And I have 10 phosphorus, so 6 phosphorus plus 4 phosphorus, 10 phosphorus, 10 oxygen there, and 30 chlorine. 6 times 5, 30 chlorine. So this makes sense now. So this is totally balanced now. Didn't ask for that symbol, so that is entirely okay there. Phew. On to the next one, we are supposed to work out empirical formula. Empirical formula is defined as the simplest whole number ratio of your atoms. Simplest whole number ratio of your atoms. So we're going to do our mole calculation. So this is hydrogen, this is phosphorus, this is oxygen. Percentage by mass, it means if you have 100 gram, then 3.66 out of 100, which is 3.66 gram out of 100 gram is going to be hydrogen there. So if I do mole equal to mass over AR, because I'm going to divide it by the relative atomic mass as I'm trying to find the mole of the atoms. So this is 3.66 divided by 1, that's the relative atomic mass from the periodic table. Phosphorus divided by 31, and then the mass of oxygen in gram, as these are percentage by mass, divided by 16 because it's the simplest whole number ratio of atoms. Definition wise, they were straight from the syllabus. And I'm going to get 1.22 there. So 58.54 divided by 16, I get 3. Okay, there's a bit running out of space there, so hopefully I can just move this up a little bit there. And 58.54 divided by 16, I get 3.66 if I round it up. So now to get the simplest ratio, I have to divide the whole thing by the smallest number. The smallest number there is 1.22, so 3.66 divided by 1.22, this gives me 3. 1.22 divided by itself gives me 1. And again, 3.66 divided by 1.22, this gives me 3. So in terms of empirical formula, it's not carbon because I'm so used to writing this carbon. So there's 3 hydrogen, there is 1 phosphorus, there is 3 oxygen. This empirical formula, H3PO3 there. Part E, now we were specifically told in this example, Y is not the same as the previous X. So this is H3PO4, different from what we got before. This relative molecular mass is 98. So your empirical formula, MR of H3PO4, so there's 3 times 1 plus 31 times 1 plus 16 times 4. Pressing down the calculator, I get 98. And we could see that the empirical formula multiplied by 1 is already 98. So therefore the molecular formula is itself because it's only 1 multiple. That means it's just multiplied by 1 times throughout. So therefore the empirical formula is equal to the molecular formula there. That's it really overall for this 12 marks question. In this question number 5, this is about contact process. There are a couple of steps here. Molten sulfur burns in air to produce sulfur dioxide. So sulfur plus oxygen giving you SO2 gas. And this next step is the reversible step, is the formation of SO3. This is step number 1. This is basically your step number 2. Your reversible changes, as you could see there, represented by this reversible arrow. And that is the step that you actually require specific temperature, specific pressure, as well as the catalyst. They want you to name the catalyst, not the formula. Although we know the formula, we've got to give the name there correctly. The formula is V2O5, vanadium. It's in the transition metal series, the first row. So it's vanadium 5 plus, O2 minus, because you have 2 of the vanadium 5 plus, you have 5 of the O2 minus. You can think about the plus 5 giving you plus 10, minus 2 5 times giving you minus 10. Charges cancel out, V2O5 there. Transition metal, oops, beg your pardon there. Transition metal there must have the oxidation number. Oxidation number represented by Roman numeral. In order to name transition metal compound correctly, must have the Roman numeral. Contact process, reversible changes, has this SO2 going to SO3 by using this compromised temperature. The pressure is not extremely high, it's much lower than the Haber process, so it's just 2 atm pressure there. Stage 3, we do not dissolve the sulfur trioxide in water straight away because it is in factory and is actually quite dangerous because it produces a lot of toxic and corrosive fumes. So instead we dissolve that in corn sulfuric acid, giving us this intermediate. I sum up all my hydrogen, I sum up all my sulfur. 1 sulfur plus another sulfur is 2 sulfur, 3 oxygen plus 4 oxygen is 7 oxygen. That is your oleum there. And oleum can then be dissolved in water and you will get your sulfuric acid. So it's like a 2-step process, but we got to balance our equation now to give us 2 sulfuric acid like that. Well, we are asked on stage 3, which is basically the formation of oleum. So that is your SO3 plus your concentrated sulfuric acid to give us H2S2O7 as stated in the question earlier. Now name the substance, not the formula. In stage 4, we convert oleum into sulfuric acid by adding it in water. So you do need water where the oleum get taken up by water to give you your sulfuric acid there. So water is the name of the substance. Now what happens when concentrated sulfuric acid is added to sugar? So we know that sugar, when you add it with corn sulfuric acid, the corn sulfuric acid is acting as dehydrating agent. Dehydrating agent basically mean it's going to take away the water. So take away the H2O. So as you take away the H2O, you're gonna take away what is this, 11 times H2O, because 22 hydrogen, 11 oxygen. So what's gonna be left behind is just carbon solid, and that is just the name of the carbon solid. Part C, we have this titration setup. This is an acid, sulfuric acid. This is a base or an alkali because it's a soluble base. And of course, potassium sulfate is a salt and water. This is your classic neutralization reaction. If you write ionic equation, then you're going to get H plus from the acid, OH minus from the base, and you're going to get H2O liquid coming from the aqueous acid and the aqueous base. Aqueous acid contain H plus, aqueous base contain OH minus. Again, that is the one and only ionic equation for every single neutralization in the world. We have potassium hydroxide inside the flask. In this kind of titration between a colorless solution and colorless solutions, you need something called indicator. So a suitable indicator would include things like bromothymol blue, phenolphthalein, or methyl orange, which is very, very common. Well, we have to do some calculations here. So first of all, calculate the number of moles of potassium hydroxide. This is to do with solution chemistry. So solution means that N equal to C times V. N is the number of mole. Concentration is mole per dm cube. How many mole dissolve in 1 dm cube of distilled water? This is volume of solution, never gas. And this is in dm cube. We also know that 1 dm cube is 1000 cm cube. So when you divide 1000 cm cube on both sides, you're going to do 1 divided by 1000 dm cube there. So be very careful. When you want to convert CNQ to DNQ, you divide it by 1000. When you have DMQ going to CNQ, multiply by 1000 there. Well, the mole of KOH there, label your stuff, label your working. So that what I have is concentration, which is 0.100 according to the question. That is in mole per DMQ. I am going to show the units so that I will be less likely to make the mistake, because now I am converting the CM cube to DM cube by dividing by 1000. The per DM cube and DM cube will cancel, and 0.100 times 25 over 1000, I get 2.5 times 10 to the minus 3. By right, this is 3 significant figures. The calculator only gave us 2 significant figures. I'm just going to add in an additional significant figure. I don't think you will get penalized if you don't, but it's just about being appropriate with the number of significant figures there. Now we have our sulfuric acid is to our KOH. If we look at the mole ratio, we have 2 mole of KOH, 1 mole of sulfuric acid, 1 mole of sulfuric acid, 2 mole of KOH there. 1 mole of sulfuric acid, 2 mole of KOH. This is from the balance equation. That is from the balance equation. Now, what is your actual amount? Our actual amount is what we want to find out. We have to find out the mole of sulfuric acid actually, and we have 2.50 times 10 to the minus 3. So we can do a cross multiply like this, meaning to say 1 times 2.50 times 10 to the minus 3 equal to 2x. So x equal to 2.50 times 10 to the minus 3, dividing that by 2, and I will get my final answer as 1.25 times 10 to the minus 3, and again that came out to 3 significant figures there. Next one, calculate the volume of sulfuric acid required. I have my mole of sulfuric acid, and this is solution chemistry, so this is another N equal to CV. The volume is equal to N divided by C, as I move the C from the right to the underneath the left. I have the mole of sulfuric acid, that was 1.25 times 10 to the minus 3. 1.25 times 10 to the minus 3, and then I divide that by concentration of sulfuric acid. According to the question, the concentration of sulfuric acid there, 0.0625 mole per dm cube. Now this volume will be given in dm cube, so be very careful there. So I'm going to write it down as 0.02 dm cube. What do they want? They want it in cm cube. So I'm going to multiply that by 1000. So that they will convert that to cm cube, and I'm just going to maintain the consistency of 3 significant figures, just like I had done earlier, because of the data given the question being 3 sig fig. So 3 sig fig there. You can also see 1, 2, 3 sig fig in the original data there, and you also had 3 sig fig there and 3 sig fig there. So significant figures, it comes down to decision making. What is appropriate number of significant figure there? So 20.0 cm cubed there. So now in part 2, we are repeating the whole same titration, same volume and concentration of potassium hydroxide. So this means that the mole of potassium hydroxide in the conical flask is the same as before. So previously you used sulfuric acid and you made this potassium sulfate K2SO4, and that's why you needed, only 1 mole of acid is to 2 mole of KOH. But now you're saying that the acid does not give you both the H plus. You're saying that the acid only give you one of the H plus, but you still have the same amount of KOH inside the conical flask. So that means when the sulfuric acid only give you one H plus to give you hydrogen sulfate, so we need twice as much. We need more H plus in order to neutralize the same amount of KOH, because now the sulfuric acid, each H2SO4 only give 1 H plus. Now previously it gave 2 H plus, so therefore we need greater mole of the sulfuric acid in this sense. And if we only give this much, we have to use double the amount, which is double the volume in this case. So therefore I'm gonna need 20.0 times 2. This gives me 40.0 cm cubed. This is saying that if the sulfuric acid acts in such a way that it gives away only 1 H plus, but we have the same amount of KOH, previously you will have, a same amount, a particular volume, which was 20 cm cubed to neutralize the KOH inside the flask. But now you have like half the amount of H plus from the sulfuric acid. Therefore, you will need twice the volume in order to give you the same amount of acid that could neutralize the KOH in the conical flask completely. In part D, so we're supposed to describe observations. Describe means you gotta write out more than just one word. When we do a flame test, this is of the cations. So that means our cation there is K plus. So you get a lilac flame color. That was the test for K plus. So lilac flame color is observed, I guess. Now you have solid copper to carbonate. Now you have 2 marks and you have 2 lines. This is an insoluble carbonate. So when it reacts with this hydrogen sulfate, potassium hydrogen sulfate, which is acidic as it contains H plus ions make it into an acid there. And acid is going to react with carbonate to give you copper 2 salt. Copper 2 sulfate is a blue solution. So we see a blue solution of copper 2 sulfate, CuSO4 aqueous, is formed. And then what else do we see? We definitely see effervescence. Why do we see effervescence? We see effervescence or rapid bubbling because, the gas, there is gas being produced. This is the usual test for carbonate, CO3 2- from practical. And also alternative to practical, reacts with acid to give you carbon dioxide gas. And then this gas turns lime water milky, as this gas is carbon dioxide. So that is if you test the gas by bubbling it into lime water. And of course we can say that the copper 2 carbonate reacts. We don't know whether it's excess acid or not, but the copper 2 carbonate will slowly dissolve into the solution that will have been acceptable as well. The next one is going to be Ba2+, which have been acidified. This is usually used to test for sulfate, which we do have. We have SO4 2- when this potassium hydrogen sulfate dissociates in water. So we get white precipitate forming. We are not allowed to use PPT other than practical papers. So white precipitate forms, as this is going to be the classic precipitation reaction. And this is including stat symbols, write ionic equation. So you have Ba2+ from the group 2 metal ions. You have sulfate SO4 2-. Test for sulfate. The sulfate came from the hydrogen sulfate dissociating in water, SO4 2- sulfate there. And it precipitates out this insoluble precipitate where the formula is 1 barium and 1 sulfate, because one of the 2+ cancel out the charge. 2- exactly, you just need 1 of each in order to give you this insoluble white precipitate. All sulfates are soluble except for barium sulfate, calcium sulfate, and lead sulfate. As part of salt preparation topic, solubility rules, barium sulfate, insoluble white precipitate, practical chemistry, test for sulfate ions using acidified barium nitrate or acidified barium chloride there. Atoms are balanced, one barium and one barium, the whole SO4 and the whole of SO4. Charges are balanced, one of the +2, one of the -2. No overall charge on the left, no overall charge for this ionic compound, precipitating out at this salt, barium sulfate. 3 marks overall, 17 marks overall for this question there. Question number 6, we have these chloroethenes. Chloroethene consists of these looking like alkene ethene, but one of the hydrogen get replaced by chlorine, and you can get it from this reaction giving you this alkene and kicking out HCl. This seems to be the opposite of addition, because when you go to do addition, you have two things added together to give you one product. So this is opposite addition. This is actually what you call elimination. Eliminate means you kick out the HCl from here, and therefore you are going to get this particular chloroethene there. Some bond energies are given. Use the bond energy to calculate this energy change. Here, this is to break the bonds. So calculate the energy needed to break bonds. So what are we breaking here? Well, if you think about it, what we are breaking here is you're gonna break the total thing. If you think about it, I mean, there are two ways of looking at this problem actually, because if you see that this one is here, 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 and here, so they are still present, okay? But I have a feeling that when they ask you calculate the energy needed to break bonds, you are breaking everything. So if you are just asked to work out the enthalpy change, which is usually the final end game of this type of questions, you could have skipped breaking down everything, because this thing, if you break this 4 pink color bond, you're going to form these 4 color bonds as well, so it's kind of cancelling each other out. But I guess because they do want you to work out the energy needed to break bonds, so I'm just going to have to break everything. So here we are breaking 1 times CC, we are breaking 1, 2, 3, 4 times CH, and we're also breaking CCl 2 times. And that would be 1 times 350, or 350 times 1, and CH will be 410 times 4, and CCl will be 340 multiplied by 2. And what are we forming? We are going to form, what are we forming? 1 times CC double bond, so that's 610 multiplied by 1, and you are forming 3 times CH, so that is 410 multiplied by 3, because there's 1, 2, and 3 CH. There is 1 CCl, so that's 340 multiplied by 1. There is also a HCl that you have formed, so there's 430 multiplied by 1. As you could see, it's going to be bond energy, energy absorbed when you break bond, minus the energy released when you form bonds. So the 4 times CH and the 3 times CH, the net result is break 1 CH. The net result of breaking 2 Cl and forming 1 CCl is you're going to break 1 CCl. And that's what I meant by you're going to cancel them out if you do them in one go. However, doesn't matter, so that's what they want us to do here. So what I'm going to do is going to add them up together. So when you add this up together, you're going to get 350 plus 410 times 4 plus 340 times 2. Let me just double check on my calculator. And I get 2670 kilojoule. So when you add them up together, you're going to get 2670. Now on the other side, when I form this particular bond, calculate the energy release. So bond making is exothermic. We don't put a negative sign because this is just the energy release when you form bond. So again, gonna add this up. So that added with that, added with that. So 610 times 1 plus 410 times 3 plus 340 plus 430. This is going to give me 2610. So 2670 bond breaking, 2610 bond forming. So enthalpy change is the total energy for bond breaking minus the energy release for bond making and I could take the difference between the two, 2670, 2610. 2670 minus 2610. And now, because this is to do with enthalpy change, I must have sign, I must have value, I must have unit there. So I put down kilojoule per mole now, because this is, enthalpy change and no longer just about energy. And this is reacting 1 mole of this, so that's why it's kilojoule per mole, because the total energy change is for reacting 1 mole of this. So it's quite simple and straightforward. It's just going to be kilojoule per mole there. It's to do with enthalpy change, so I must have kilojoule per mole as stated, sign, value, and also unit there. Now decide whether this reaction is exothermic or endothermic. It is endothermic. Give a reason. Well, we saw the sign. We saw the sign there. The sign of the enthalpy change. The sign of the enthalpy change is greater than 0. It's positive. So it means more energy is needed. More energy is absorbed to break bonds compared to the energy release to make bonds, to make new bonds or to form new bonds, because big minus small give you positive result overall. Part B, this is part of a synthetic polymer. This is very clearly an addition polymer, and that's because we don't see any ester, you don't see any amide. So ester and amide are hallmarks of your condensation polymer. So this means that this must be addition polymer. How many monomer units? That are needed to make the part as shown above? We could see that here to here, that is your repeat unit, because you could see from there to there, that is 1 repeat unit. And as such, you will see that there is another repeat unit there. So this is the second repeat unit. And therefore, how many units? There's 2 monomer as shown here. If you want 3 repeat unit, you draw another equivalent one. And now, of course, as usual, draw the monomer, but show all the atoms and all of the bonds. So be very careful here. We would be thinking that we would add the double bond here and here. And as such, I would just get carbon, and then a hydrogen. So that would be the CH2. There is 1 hydrogen here. And now I can draw my carbon. And slowly running out of space here, so perhaps I move there a little bit. And now this is C2H5. So this is bonded to another carbon. So there's hydrogen and hydrogen. Because carbon form 4 covalent bond, 1, 2, 3, 4. So this carbon also form 4 covalent bond. I show all the atoms, as you could see. 1, 2, 3, 4, 5. 2 carbon, C2H5. This is my double bond from the alkene. 1, 2, 3, 4 covalent bond on this carbon. 1, 2, 3, 4 covalent bond on this carbon there. Now, having drawn that, you could hopefully see the naming. If I name this is the important carbon, starting with the lowest number possible, because if I go 1, 2, 3, 4, the alkene is at 3, but here this is 1, 2, 3, 4, the alkene is at 1, so this is what you call build, because 4 carbon. This is build 1 int, because the position of the alkene is at carbon number 1. Now you don't have to draw the same way as I did. You could draw them a lot nicer if you want to. So this way you could see that that is going to be your build 2 int, and what I've drawn there is just basically the same thing. It's the same as this straight chain which I have drawn, because there's also 1, 2, 3, 4 build 1 int C4H8, C2H5 there, plus 2 carbon C4, 5, 6, 7, 8, C4H8, build 1 in there. Now state the empirical formula of the polymer. Because it's an addition polymer, so one of the characteristics of addition polymer is that it has the same empirical formula as the monomer. And the reason is because you are not losing any product, you are just adding them together. So C4H8 can get simplified to CH2, the whole thing, multiple of 4, but this is just the multiple. So inside here, this is the empirical formula, CH2, which is the empirical formula of all alkenes, having started from CnH2n. You divide by n both sides, you're going to get with CH2 as your empirical formula for every alkenes there. Part C, proteins are natural polymers. So proteins are broken down into amino acids. This process is called hydrolysis. You need the presence of water as well as heat in order to break up. Lysis, just like electrolysis, here is just breaking up proteins in the presence of water. Name this process. This is hydrolysis of proteins. Name two types of substances to break down proteins into amino acids. So to do hydrolysis, you can use dilute acid. So dilute, they want the name, dilute hydrochloric acid. Two types of substances. Two types, not the name of the reactant itself. You can use dilute acid or you can use dilute base. So acid hydrolysis, that is the name of the process. It's going to be so much faster than just using water, of course. Then using the base is going to give you your base hydrolysis. These are not the answers. These are the name of the process, because what you need will be the acid or the base. They ask for the type of substances. I don't think they will be asking for the name of the substances. They ask for the type of substances there. Now, amino acids are colorless. When you do the separation techniques, you are going to do the paper chromatography techniques. So that's supposed to be what I fill in onto the space, and that is exactly what I'm going to drag this down there. So you're going to do the chromatography techniques. This is based on the solubility of the substances, the amino acids in the solvent of choice. The problem is amino acids are colorless. So name this substance. Well, you need this thing called locating agent. Because amino acids are colorless, you cannot see them unless you spray it with this locating agent, which is going to make the spot come out as colored, and you'll be able to measure the RF value. Give the symbol of the RF value to determine the identity. That is called RF. That is basically retention factor. They want the symbol, they don't want the full definition, they don't need the formula, but the formula is basically the distance of your solute. This is from the baseline, from where you draw the line using pencil, the baseline, and then you talk about division of the distance of solvent from baseline, so from the start all the way to the solvent front. And you're supposed to take out the chromatogram before it reach all the way to the top of the paper, so that you don't overshoot it and you'll be able to reliably get the distance of solvent all the way from baseline to solvent front there. Part D, proteins are natural polymers. Proteins contain amide linkages. Amide linkages is C double bond O and H like this, and then carbon form 4 covalent bond, 1, 2, 3, so it extend on this way. Nitrogen form 3 covalent bond, so 1, 2, it extend this way. So this whole thing is the amide linkage there. Having got the amide linkage, we know that this is the bond, the new bond that you form. So this part that contains C double bond O, they come from the carboxylic acid having lost the OH, and the other side is the amine. The amine will have lost the H in this condensation reaction. The type of reaction is called condensation reaction. Name a synthetic. Synthetic will mean that it's man-made, unlike the natural proteins, natural polymer, natural amide, which is proteins there. So naming this will be like nylon. Identify the two functional groups in order to produce synthetic polyamide. I think I just did that above. You must have this carboxylic acid group, you must have this amine group, but they want to produce synthetic polyamide, so you need dicarboxylic acid. So you can include the di there, but essentially the name of the functional group would be carboxylic acid. The name of the functional group would be amine. The di basically means you are going to have both sides that have carboxylic acid, both sides that have the amine, that is NH2, but that is man-made. But do not forget about our natural amino acid. They contain the amine, they also contain the carboxylic acid. So I could be starting with things like, NH2 on one side and CO2H on the other side. That is the idea of amino acid, contain both the amine and also the acid. So amino acid there. So carboxylic acids without the di should have been alright, I think, because they just want the functional groups. In reality, to give you the polyamide, you must have either dicarboxylic acid or diamines, diamines. But then they want synthetic, so you cannot say amino acid. If you say amino acid, that would be wrong because of the word synthetic there. That's it for this overall 18 marks questions. And I believe that that's the end of this paper 43 for the November 2022 Cambridge International IGCSE Extended Chemistry paper. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. And to let friends, relatives, chat group, juniors and seniors and teachers know about the packages available with all these wonderful tutorials at a wonderful price. So get in touch if interested to get more tutorial videos at a great price. Thank you for watching. See you in the next tutorial video.